So in this video, we'll be looking at the flexural design of singly reinforced beams. As an engineer, you might be facing two kinds of problem. The first kind of problem is that you're assessing the capacity of a given beam. In this kind of problem, you'll be given the dimensions of the beams, the overall depth of the beam, width of the beam, effective depth of the beam D, and also the area of reinforcement AST as well. So you know all the dimensions of the beam, and you are required to find what is the flexural strength of this beam. So we have already seen an example of how to do this, and the steps to do this is that we first assume the type of failure mode, that is either tension failure mode or the compression failure mode, and then we check our assumption if that assumption is correct or not, and then we find the flexural strength of the beam based on the KU that we calculated. The second kind of problem is the design problem. In this kind of problem, we are given the loads that are acting on the beam, and then based on the loads we have to calculate what is the strength required for the beam to carry the loads, and based on the required strength we have to design the beam. That means we have to find out what is the depth of the beam required, what is the width of the beam, and what is the area of the steel requires, and also what is the effective depth required. So in this kind of problem, we are given the required strength and we have to find out the dimension of the beams. So before we go into the design of the beams, there are a couple of things we need to understand, and the curvature is one of them. When the beam is subjected to flexural moment, or the bending moment, the flexural deformation is often recorded as the curvature of the beam itself. Curvature is basically the rotation per unit length. The rotation of the beam per unit length is what we call as curvature, and denoted by kappa. That means the kappa is the rotation delta theta per unit length, that is delta x. Now in this beam, this beam is subjected to the bending moment M, and with this one there is a curvature, that is bending in the beam, and that curvature is defined as delta theta over delta x. Now if we look into this small element EFGS, we zoom it here. As you can see, because of the bending moment, the topmost fiber ES is in compression. That means it has shortened a bit, and that shortening is basically the compression strain multiplied by delta x. The delta x is the original length of that element. Similarly, the bottommost tension member FG is subjected to tension, so it is extended here. So the delta x, the original length of this member was delta x, but due to the strain, the tensile strain epsilon st, the member is extended to delta x plus epsilon st delta x. So in this case, from this diagram, we see that the rotation delta theta is denoted by the compression length here, the epsilon naught, the compressive strain multiplied by delta x, plus the tensile strain multiplied by delta x, and divided by the effective depth of this beam. So this equation denotes the rotation of this beam delta theta. Similarly, if you simplify this one, what we see is that the curvature of the beam kappa is now delta theta over delta x. Now putting back the value of delta theta, we will simplify it as epsilon naught plus epsilon st divided by d. Now if you look at the strain profile, epsilon naught plus epsilon st divided by d is what we call as the curvature. And more simply written, if we write it more simply, you can see that the compressive strain divided by the depth of neutral axis from the top compression fiber, that is epsilon naught over dn, is the curvature of the beam. So this is important to know this kind of the definition of the curvature, because we'll be using this definition to define what is the ductility of the beam. As we have talked about ductility in other occasions as well, ductility is basically a deformation a large deformation that the member can sustain without breaking. So ductility allows deformation to occur in the member under overload conditions before it eventually fails. We'd want our structures to be ductile because it gives the warning to the occupants of the impending failure. And as we saw earlier, the under reinforced beams are more ductile than the balanced failure mode or the over reinforced failure mode. So we want our beams to be under reinforced failure mode. Now, if we draw the moment curvature diagram of the beam, so if we keep on drawing, so the beam is subjected to bending moment, and then we are drawing the moment curvature curve. As you can see here, as the moment increases, the curvature increases as well up to point C, where the crack will occur in the beam, and we know that that moment which causes the first crack in the beam is called as a cracking moment. And if you further load the beam, it will go into the nonlinear region, and here at certain point Y, the beam will start to yield. That is denoted by My, the yielding moment, and the corresponding curvature is denoted as kappa Y. Now, if we further load the beam, at certain point the beam will fail, and that is corresponding to the ultimate moment of the beam, and the corresponding curvature is the kappa U. Now, the ductility of this beam is defined as mu, which is equal to the ultimate curvature at the ultimate moment, kappa U, divided by the curvature at the yielding point, that is kappa Y. So kappa U divided by kappa Y is what we define as ductility, and how we measure the ductility. Again, here kappa U is the curvature at the ultimate failure moment Mu, and kappa Y is the curvature at the yield moment My. And we know that the curvature at the ultimate moment is, from the previous slide that we saw, it is the compressive strain at the ultimate crushing of the concrete, that is 0.003, divided by the neutral axis depth from the topmost fiber D, and that will give you the ultimate curvature of that beam. Now, to design the beam, we would need to first understand where our reinforcement will be placed in the beam, and it is a very important step. Now, if we look into a uniformly distributed load on a simply supported beam like this one, as we know, this uniformly distributed load will cause a deformation in the beam like this. That means there is a compression at the top and there is a tension at the bottom. So we know that concrete is very strong in compression, so we don't have to worry about the compressive stress. But for the tensile stress, to take this tensile stress, we have to put the reinforcement at the bottom. Whereas in the cantilever beam, again loaded with the uniformly distributed load, we know that the deformation of the cantilever beam will look like this one, with the tension at the top and compression at the bottom. So to take this tensile stress at the top, you will need to have a reinforcement at the top in the cantilever beams. Now, this is an example of cantilever beam. As you can see here, there is a cantilever portion here. So the reinforcement for the cantilever beam has to be at the top because there is a tension coming at the top. So for this beam, the reinforcement should be at the top. Now for the continuous beam, as you know, for the continuous beam, for the mid span, there is a negative moment here, and the middle span, in both the spans here, there are positive moments. So if you draw a bending moment diagram, positive moments at the mid span here and positive moment at the mid span here, and at the middle support there is a negative bending moment. So to take that negative bending moment, if you want to put a reinforcement, it has to be on the top at the middle support because there is a negative bending moment here, and at the mid support here the reinforcement has to be at the bottom because it is at the tension is at the bottom, and also here the tension is at the bottom, so the reinforcement here also should be at the bottom. Only at the middle support, where the tension is at the top, your reinforcement should be at the top as well. Now for the flexure design of a single reinforced beam, we follow the ultimate strain design equation. So we know that the ultimate strain design equation is represented by this. That means the design strength phi RU should be greater than or at least equal to the factor load effect H star. Now, if we are concerned with the bending, when we are concerned with the bending moment, it can be represented as phi mu should be greater than or equal to m star. In this equation, phi mu is the design strength, design bending moment, and m star is the moment demand to meet the given load. So m star is the moment due to the factored load, or also it's a required ultimate moment or the moment demand due to the external load. And mu is the nominal moment capacity of the section, and phi is the strain reduction factor, and we know that it can be obtained by table 2.2.2 for AS from AS 3600. So phi mu is the design moment and m star is the moment demand. So when we are designing a reinforced concrete beam, you have an option to choose the dimension. When you have an option to choose the dimension, you will make sure that the beam is falling in a ductile manner, that is in a under reinforced manner. So when you are designing a beam, you will choose the KU value, that is the neutral axis depth parameter, smaller than 0.4. If it is the K value we choose less than 0.4, then we can make sure that our beam is failing in the under reinforced or the tension failure mode, which is a ductile failure mode. But usually, again, to be in the safer side and to make the section more economically efficient, for design we usually use the KU, limit the KU value between 0.15 to 0.3. And also when designing a reinforced concrete beam, we have to make sure that there is enough amount of reinforcement as well. So AS 3600 or the design code prescribes you the minimum amount of reinforcement as well. So the AS 3600 clause 8.1.6.1, if you look at this clause, it prescribes that the ultimate bending moment has to be at least greater than 1.2 times the cracking moment. If your ultimate moment is smaller than 1.2 times the cracking moment, there is a risk of fracture of the steel itself, which causes the sudden collapse of the beam. So to prevent those kind of fracture of the steel and the sudden collapse of the beam, the AS 3600 prescribes that for a rectangular beam, the reinforcement should be at least, the area of reinforcement should be at least equal to this given by this equation. Now this is given in clause 8.1.6.1.2 in AS 3600. In this equation, AST is the total area or the minimum area of the reinforcement required in the beam. Here capital D is again the overall depth of the beam, small d is the effective depth of the beam, F-CT.F is the tensile strength of the beam, FSY is the yield strength of the beam, and B and D are again the dimensions of the beam. So your area of the reinforcement that you provide in the beam should be at least greater than this value. Also, we saw earlier that from the durability requirement also prescribes some minimum effective cover and minimum characteristic strength as well. So AS 3600 table 4.10.3.2 prescribes the minimum characteristic strength FC- and the cover values for different exposure condition. For example, for a B1 exposure condition, the minimum concrete strength required is 32 megapascal, and the minimum clear cover required for the beam is 40 millimeters. So what it means is that, what clear cover means is that the distance of the reinforcement from the soffit of the beam, the base of the beam, should be at least 40 millimeter. So if you add half the diameter of the bar, then that you can get an effective cover that is required for the B1 exposure condition. So similarly for B1 exposure condition, when you are using 40 megapascal concrete, your minimum clear cover required is 30 millimeter. Now, when you are designing a single reinforced beam, first you have to draw a stress, strain, and force profile like this one. So this is the dimension that you want. and AST is the area of the steel required. This is stress profile and the force profile. Now the ultimate moment of this beam can be obtained by taking a moment about point T in this force diagram. As you can see, the ultimate moment can be obtained by the compressive force C multiplied by the lever arm Z. So here the ultimate moment mu equals to the compressive force C multiplied by the lever arm Z. And we know that the compressive force is the integration of this equivalent stress block, which is alpha to FC dash multiplied by gamma ku d over 2 gamma ku d and multiplied by the B, that is C. This is give the total compressive force. And the lever arm jet is basically the effective depth of the beam minus this small portion, which is represented by gamma ku over d, gamma ku d over 2, which is given by here. So your ultimate moment is given by this equation, which we are familiar with already. Now for the design moment capacity, you have to multiply this mu with phi. So from the ultimate strain design equation, it says that phi mu should be at least greater than or equal to m star, or the moment demand. So putting back the value of mu from here to this equation, it boils down, we can simplify this equation to here. So it will give us BD square should be at least be greater than this parameter. Now in here, we do not know B yet. We do not know the D of the beam as well. And also we do not know Ku. But as we know that to get the ultimate moment capacity in a ductile region, the beam has to be designed as an under reinforced beam, and to make the beam under reinforced, we have to keep the Ku between 0.15 to 0.3. So keeping Ku between 0.15 to 0.3, we plug back the value of Ku here, and we can obtain B and D. Again, there are two unknowns in one equation, so we have to assume one of the values to get another one. So if you assume the value of B, say B is 300 millimeter, then you can find the corresponding value of D. So once you estimate the B and D for the beam and Ku value as well, then you can find the area of steel using the horizontal equilibrium of the forces. That is, the tension force should be equal to the compression force. Again, the tension force is equal to AST multiplied by AFSY, because we are choosing the Ku value less than 0.4. So definitely it is a tension failure mode. So we can use stress in the steel as FSY. Now again, this is the compressive force in the beam. So from this equation, we can find what is the area of steel required. So all of these parameters are known. So we can find out what is the area of steel required for that beam. So provide that area of steel required in the beam, but we have to make sure that the dimension, the diameter of the bar you chose are available in the market as well. So with reference to the bar diameters available in the market, you will choose the number of bars to meet this area requirement. And you also have to check for the minimum reinforcement that is required. So as I mentioned earlier, once you find the area of steel, you have to make sure that that area of steel is at least greater than this value prescribed by the code. Once you find area of steel, the dimension of the beams, then the final step remaining is to check the design. So we have provided the area of steel. So using the actual value of area of steel, now we can find out the actual value of Ku. And then we have to check whether our assumption that it is a tension failure mode is correct or not. So you check the strain in the steel and making sure that it is greater than 0.0025. That is the yield strength of the steel. Once it is proved okay, then we can proceed to find out what is the design moment capacity, that is phi mu, and we have to ensure that phi mu is greater than or equal to m star is satisfied. So to summarize once again all the design steps, step 1, you have to find first the moment demand m star based on the factored loads that you have on the beam. So secondly, you will choose Ku value between 0.15 to 0.3 to make the beam fail in the tension failure mode or the under reinforced failure mode. Step 3, based on the value of Ku you chose. Find out the dimension of the beam, that is the width of the beam, the effective depth of the beam, and the overall depth of the beam using this equation. So using this equation you can find out the B and D once you take the value of the Ku between 0.15 to 0.3. So once you find B and D, you can compute the area of the steel required, that is step 4. So that can be done by equating the tension force equal to the compression force. From this equation you can find the area of steel required. So once the area of steel is required, you check the number of bar diameters available in the market and find out how many of these bars are required to meet this area of steel. And final step, as I said, is to check the design. That means using the actual area of steel that you have provided now, find out the neutral axis depth parameter Ku and ensure that Ku is less than 0.4, is still less than 0.4, and then find out the phi u mu factor, that is the design moment capacity, and ensuring that phi mu, the design moment capacity, is at least greater than or equal to m star. And the final step remaining is to draw the dimensions of the beam then as you calculated. So you have found B, overall depth D, the effective depth D, and the area of steel. So you have to draw the cross section as well as the elevation of the beam as well. Now, in this example, what we have seen is that we were given the moment capacity required, that's m star, and from using that m star we designed the beam, that is we found out B, D, and ASD. So we have the freedom to choose D and the width of the beam and the area of steel in this case. But sometimes B and D, that is the dimensions of the beam, can be fixed by other considerations. For example, for a car park, the architectural requirement can fix the depth of the beam so that there is enough clearance for the cars to come in. So in that case, B and D, that is the width of the beam and the depth of the beam, are already prescribed to you. In that case, what you do is you proceed by finding out the approximate area of the steel, because B and D is already given to you. So you find out the approximate area of steel required and then you proceed to design the beam. So in this equation, to find the ultimate moment capacity, we know that you can take a moment about point C. So it is the ultimate moment capacity is the tension force T multiplied by the lever arm Z. So the tension force T multiplied by the lever arm Z. And the tension force T is nothing but the area of steel multiplied by the yield strength of the steel, that is 500 megapascal. Now for this lever arm, because we do not know the Ku value here, so lever arm, we can simplify it as the depth of the lever arm can be simplified as 0.85 times the effective depth of the beam. This is just an approximate value. We again will calculate more detailed value later on. So to start with, we can use Z, that is the lever arm, as 0.85 times the effective depth D. So if you put Z as 0.85 times effective depth T, you know everything in this equation. You can find what is the area of steel required. So the area of steel required is m star over phi FSY into 0.85 D, which is Z here. So this will give you the approximate area of the steel required. So once you find the area of steel required, you can check if the Ku value that you obtain using that area of steel is less than or equal to 0.4 or not. If you ensure that it is less than 0.4, then you have a ductile beam, and then there is no issue with that. So again, using this trial area of steel that you provided, find out what is the Ku, that is the actual value of Ku that you are providing in the beam, and you need to confirm that Ku is less than 0.4. Now, if KU exceeds 0.4, because B and D is already fixed for you. So and you calculate the value of AST required from the moment perspective, and when you go on to find KU, you find out that KU is greater than 0.4. That means it is going into the brittle failure mode, or the overly reinforced member section. So in that case, you can change the dimension of the beam, which is restricted in this case, but other thing that you can do is you can go for a doubly reinforced section. That means you provide the reinforcement not only at the bottom but at the top as well. So that will also improve the ductility of the beam, or change it from the compression failure mode to the tension failure mode. And finally, again, you need to do the design checking, find out the actual value of phi mu, and ensuring that phi mu should be greater than or equal to m star. And of course, the detailing is required. So a couple of things to keep in mind when you are talking about the detailing. So you do not put the reinforcement arrangement like this one, because that will increase the distance of the concrete face here from the reinforcement, which can create the cracking problem here. So instead of putting the reinforcement like this one, we need to put the reinforcement more uniformly distributed like this one, so there is not a big gap from the face of the concrete to the reinforcement surface. This is the minimum dimension of the spacing required between the bars from American Concrete Institute code. As you can see here, the clear distance between the two bars is required, given by these four parameters. So it should be greater than the bar diameter dB, 25 millimeter, that is usually the aggregate size, 1.33 times the diameter of the coarse aggregate, or the diameter of the vibrator itself, to make sure that the vibrate can penetrate through it. And also the code prescribes that the minimum distance of the steel from the side of the beam should be at least 40 millimeter. And if you are using two layers of the bar, the clear distance between the bars should be at least 1.33 times the diameter of the coarse aggregate, just to ensure that the aggregate can pass in here, or 25 millimeter, whichever is the larger. So this is the specifications from American Concrete Institute code. Now for Australian code, it prescribes that the clear distance between the reinforcement bars should be at least greater than 2 times the diameter of the bar that you are using. So if you are using 20 millimeter bars, so the clear distance between the bars should be at least greater than 40 millimeter. And on the other hand, code also prescribed for the crack control of the beams, it prescribed the maximum distance of the reinforcement from the bottom of and the sides of the concrete. So AS3600 prescribes that the distance of the center of the reinforcement from the bottommost fiber of the concrete should be less than or equal to 100 millimeter. Same from the side as well. So the distance from the side of the beam to the center of the reinforcement should be the maximum should be 100 millimeter. So you should keep it less than 100 millimeter. And again, for the crack control, the distance between the reinforcement, the center to center reinforcement, should be less than 200 millimeters. So instead of just providing two large bars to meet the area of reinforcement required, you are better off putting smaller number of bars well distributed throughout the beam, so that you can control the cracks as well. And in this figure, as you can see, if the beam is very deep, so apart from providing the tensile reinforcement, you need to provide the side reinforcements as well. Though the side reinforcement, you may ignore it while designing the moment capacity of the beam, but you need to provide it for the crack control. So if the overall depth of the beam is greater than 750 millimeter, then the code prescribes that you need to provide either N12 or N16 at 200 millimeter distance or 300 millimeter distance maximum. So you need to keep this detailing in mind when you are designing the concrete beams.